Hello friends, welcome to this chapter of our discussion on thermodynamics. Herein we will see the third law of thermodynamics. Before jumping directly into the third law, I should introduce you the statistical aspects of entropy. Let's imagine this chamber of volume V1 occupies just two molecules of a gas. What could be the probability that one of those molecules is found within this volume? That is maximum probability 1 because at any time both these molecules are within this huge volume V1. Now, I consider only half of the volume V2 of the chamber, and what could be the probability that one of these molecules is found within this particular half of the chamber? That is half of the previous probability, that with the other half probability I can have the molecule in the other half of the chamber. So the probability is reduced. Now I want both those molecules within this small volume V2. Correspondingly, the probability that both these molecules are present within this volume V2 will be even halved. So if I've got 4 molecules within this volume V2, then it is again reduced the probability. So the probability we can see is a function of volume and the number of molecules. So I can relate the probability of finding this n number of molecules within this given volume V2 as V to the power n. Now let's consider this small chamber of volume V2 and my gas is expanding to a larger volume V1. So what is happening in terms of probability is that the system is moving from the low probability situation to a high probability situation. That means the spontaneous expansion of gas from this small volume V2 to the large volume V1 here is occurring in the direction of high probability. So we can attribute the spontaneous changes or the direction of spontaneous processes to be in the direction of high probability. We know that the direction of spontaneous process is the direction of increase in entropy. So relating those two, we can reach a relation between the probability and entropy through the Boltzmann constant Kb, named after Ludwig Boltzmann, who is the pioneer of statistical thermodynamics. And in terms of the measurable quantities, volume and the number of moles of the gas is present, you have got entropy to be Kb logarithm of V to the power n. Now, we have got the system of volume V1 occupying n number of molecules inside. Then the initial entropy can be given in terms of the initial probability, and when the gas is expanding to a larger volume Vf, the final entropy can be given in terms of final probability. So the change in entropy accompanying this process of expansion can be given in terms of probability like this, and in terms of volume and number of moles you get this relation. And we know that the Boltzmann constant is related to the universal gas constant through the Avogadro number N0. Therefore, you can reach the delta S, that is the change in entropy in terms of the initial and final volumes at constant temperature during the process of expansion. And now we need to see these two terms, macrostate and microstate. Macro and micro, in the general context, we understand it to explain the size of things. But here, macro and micro does not really describe the size of something, but let's see what it is. We've got a system of a chamber occupying n molecules of gas inside. This is the macrostate described by various thermodynamic variables like volume, pressure, temperature, enthalpy, internal energy, etc. etc. This macrostate, which we can really visualize, this bulk stage of the system is called macrostate, and as long as you don't change any of those thermodynamic variables, or as long as you don't demand heat or work from the system or to the system does not change over time. But we know that the molecules are in constant motion. The motion can be translational, vibrational, rotational motions of the atom inside. Even the solids have got those kind of motions. Of course, they don't have significant translational motion, but constant rotational, vibrational motions. There is high degree of molecular motion inside the system. Now, suddenly I freeze the system and then I get an image like this. That is, at a given instant, my system is described by this particular distribution of molecules in the space and the associated distribution of energy. At this particular instant, the system is described by this particular distribution of molecules, that is the position of molecules and their velocity or momentum. So position and momentum are the terms within classical thermodynamics, but the quantum mechanics talks in terms of energy and time. So do we. So at a given instant, when you look at the system, you've got a given distribution of energy among those molecules. And in the next instant, when you look, you have a different distribution. And in the next instant, you have got another distribution and this changes. Whenever you look at the system, this changes. And that instantaneous photo of the system is called microstate. So at a given instant, what is the distribution of energy within the molecule? That is called microstate. Microstate characterizes the distribution of energy or dispersal of energy. As the dynamicity of the system increases, the degree of motion within the system increases, you've got larger and larger degree of energy distribution or dispersal, and therefore you've got larger and larger number of microstates, which describes the macrostate of the system. So it is right to imagine that a huge number or huge collection of microstates will ultimately describe the macrostates of your system. And therefore, we can see that the energy dispersal can be related both to the number of microstates that describe the system and the entropy, because entropy is associated with the dispersal of energy. So we can see the relation between number of microstates and entropy again in terms of Boltzmann's constant. Here your system, the macrostate, described by the small number of microstates Wi in the beginning, is associated with entropy Si, and when it expands to a larger volume, the new entropy, the final entropy, is described in terms of a new number of microstates, an increased number of microstates, because when the gas expands, there is an increased degree of motion or increased dynamicity within the system. Therefore, the expanded system can be described with a larger number of microstates. Therefore, the change in entropy during the process of expansion can be given in terms of the change in number of microstates when the system moves from lower number of microstates to a higher number of microstate situation. So we can say that positive entropy associated in a spontaneous process or the direction of spontaneous process can be in the direction of higher number of microstates describing the system. Walter Nernst, in the early beginning of 28th century, proposed that entropy change in any physical or chemical transformation at absolute zero temperature is zero. That is, as temperature approaches the absolute zero, the change in entropy in any physical or chemical transformation occurring at this temperature will be zero. Let's consider a perfectly crystalline substance. Such a substance is highly ordered. There is no dynamicity at all, no molecular motion within the system. Even the vibrational and rotational motions of the atoms are assumed to be absent at this absolute zero temperature. Therefore, we can say that the system with no degree of dynamicity can be described by a single microstate. That is, at whatever instant you are looking at the system, you get the same image, or all the instantaneous photos look the same. That means the same state, the same microstate describes the macrostate. That means W, the number of microstates, is 1. Therefore, you reach that the entropy of the system is 0 at absolute zero. And this observation or this proposal by Nernst gave way to the third law of thermodynamics. And let's now see the third law of thermodynamics is there. The entropy of a perfectly ordered crystalline substance at 0 Kelvin, that is absolute zero, is 0. So using this information to calculate the entropy of a system at any temperature T2, assuming that the T1 temperature is the absolute zero, so you get the value 0 here, the first term on the right hand side. Therefore, you can relate the entropy of a system at any temperature with the heat capacity, assuming that the T1 here is the absolute zero. Actually, this equation we have seen already before when we discussed the thermodynamic entropy in terms of a reversible heat. But although third law says that entropy at absolute zero is a zero, we can see there not all substances are perfect crystals when they are cooled to absolute zero. For example, carbon monoxide, the diatomic gas at room temperature. Here carbon is described in black and oxygen is red. When you have got a particular arrangement of carbon monoxide in its crystal when it is cooled. And our expectation is that at absolute zero, the system is having no dynamicity, no molecular motion. So only this particular microstate is describing the macrostate of the system. But we can see that at least one more different orientation is possible for carbon monoxide. That is, at least the direction of alignment of the molecule can change. So at least 2 to the power n microstates are possible to describe the system if n is the number of molecules. So you can see that in terms of the number of microstates, entropy is given like this, positive number, but not zero as predicted by the third law of thermodynamics. So there is a discrepancy. When you look at the real case, in reality, not all substances are perfect crystals and not all are described by a single microstate. So more than one microstates describe the system even at the absolute zero, and this discrepancy between the third law and the reality is called residual entropy. That is the third law entropy, that is the entropy described by the third law at absolute zero is zero. But we have seen that at absolute zero for carbon monoxide, for example, has got non-zero entropy. And that entropy difference is called a residual entropy. So that entropy of your system calculated for a particular temperature based on third law, that entropy is called third law entropy. Otherwise, when you say entropy, it takes into account the residual entropy also. And you can see that for crystalline ice, the residual entropy is 3.4 kilojoules per mole. And that's about the statistical aspects of entropy, entropy in terms of probability and microstates, and the third law of thermodynamics and residual entropy. Now let's close for the time being, and the next big thing to come up is free energy functions, the forms of energy which can be utilized for useful work. Thank you until then.